Hi, Ray Poynter here, and welcome to How to Use Correlations to Find Stories in the Data. So today's plot, we're going to start with a little bit about what is correlation, then the causes of correlation, before proceeding on to have a look at how we can use correlation to help us find stories. And then I'm going to take a brief look at what comes next after correlation, and then we'll take question and answers. So a little bit technical to start with. Correlation measures the linear association between two metric scales. So we're looking for relationships that are linear. As one thing changes, so does a second thing. And we're looking for a relationship between scales like age, income, percentage chance we will use something, a 7-point scale, a 5-point scale, a 10-point scale, something that is a metric scale, and we're going to have two of them, and we're looking at the link between them. There are other correlation measures that use non-metric scales. They are much less frequently used. Correlation produces a number, we call it the coefficient, and its entire existence ranges from -1 to +1. It's not a very long way to go, and you're going to see why later it has that range. And +1 is a perfect correlation. Every single change in X causes a scaled similar change in Y. 0 means there is no relationship between X and Y, or the two variables we're looking at all. And -1 means there's a perfect negative correlation. And I'll show you an example of a perfect negative correlation in a moment. Now, we tend to use the letter R, either a small case r or an uppercase R, to refer to the most common form of the correlation coefficient. So when you see R or R squared, then you know that we're talking about the correlation coefficient. We're talking about the linear one. We're talking about the one that uses scales. And we will often square the correlation coefficient to get a number we call R squared. And we often express that as a percentage. And again, I will show you more about that in just a moment. So here is an example of what perfect correlations look like. The one on the left is R equals 1. There is a perfect correlation between X and Y. Every time X goes up, Y goes up. And it goes up in the same ratio each time. On the right-hand side, we have R equals -1, a perfect negative correlation. If we drive a car, the amount of fuel in the tank is negatively correlated with how far we have driven. The more we drive, the more fuel that we've used, and down goes the level in the tank until we add more fuel. Now, of course, there are minor variations depending on how we drive, but on a long journey, that's going to be pretty close to a perfect negative correlation. This is a strong correlation. We don't get perfect correlations normally in data that we look at. If there is, it's normally some sort of data error or processing error. Even 0.9 is not common, and this is a really strong relationship. You can see how close to a central line all of those dots are. As X is going up, Y is going up. Not always by the same amount, but by a fairly similar sort of ratio and percentage. So when we look at those, the first things we notice is that 0.9 actually doesn't mean anything. It's produced by the statistics. We'll type it into a calculator. We will ask Excel to tell us it. We'll be using SPSS or Q, and we'll get it as a piece of feedback, but it's not very intuitive. So that is one of the reasons why we often square the R value to get R squared. We also call it the variance, because it is the proportion of the total variance that's stored. So in this case, we've got X and we've got Y. And if we add up all the movement there is on that page, all the left-right movement, that's the X movement, all the up-down movement, that's the Y movement, that's the total amount of variance. And we put that on the bottom of our equation. And on the top of the equation, we put how much of that variance is shared by X and Y. And of course, if they share all of the variance, we are going to have the same number on the top and the bottom, and that's why it's going to equal 1. If they have the same amount of variance, but it's in the opposite direction, then we will have -1. And that is why those values range from -1 to +1. It's the ratio of all the variance those two numbers have in common, divided by all of the variance they have full stop. So if we take 0.9 and we multiply that by itself, which is what we do when we square numbers, we get 0.81. And when we're talking about R squared, we very often write it as 81%. So 81% of all the variance on that page is shared between X and Y, and 19% of the variance is not shared. We should always think about the not shared proportion as well. So in real data, the sort of data we have from market research, a correlation coefficient of 0.7 is pretty strong. But if you look at that page, you can see how many data points are not very close to a line running through the middle of them. So the R squared, if we have 0.7 as correlation coefficient, is 51%, or let's call it half. Half the total variation is shared, and half the total variation is not shared. And that's an important thing to remember. If in our behavioral data, our market research study, our satisfaction study, we got correlation coefficients of 0.5, they will often be worth looking at. They're notable. We'll also remember, however, that the R squared for those is 25%. So 25% of the variation is shared, so they've got something really important that is linking them, but 75% is not. And again, if you look at the pictures, you can see that there's a lot of dispersion. There is a bit of a sense of going in one direction more than the other, but there's a lot of spread out data there. Now, in the real world, a zero correlation is pretty rare. The way we do measurements, so we'll have a 5-point scale or a 7-point scale, tends to mean one end of the scale is good, one end of the scale is bad. We tend to find that people are generally evaluative towards one direction or the other. So that will tend to make some correlation in the data. And when we've chosen things to include in the study, they often have something in common about them. So we're doing a retail study, we've got lots of retailer attributes. Well, obviously there are things they have in common, otherwise we wouldn't have selected them. So it's quite rare to get zero correlations in the data, but we certainly get a lot of values that are close to zero, which means that there is no correlation between these two attributes, no linear correlation between these two attributes. There could be some other types of relationship. So that is what correlation is, and it will become even clearer as we go through. But what causes correlation? Well, perhaps the most famous thing about correlation is this statement: correlation does not imply causality. Just because X is correlated with Y, it doesn't mean that X causes Y. So if X is correlated with Y, then usually we can say one of the following. Perhaps X causes Y, or perhaps Y causes X, or perhaps X and Y are both caused by a common agent Z, or X and Y both cause each other in a feedback system, or it's just chance. Now let's just start with that just chance. One of the things that Nate Silver, the really good guy with predictive analytics who wrote The Signal in the Noise, has made this point that as we get more big data, a bigger and bigger percentage of the correlations we see and the relationships we see in the data and the patterns we see in the data will be chance. So we are going to have to be more and more careful about looking at chance. What about this X and Y are both caused by a feedback system and X and Y are both caused by a common agent? Well, maybe we have a really hot summer. That hot summer causes an increase in the number of ice creams that are purchased. We also see an increase in the amount of sun cream that is purchased. There will be a strong correlation between the amount of ice cream purchased and the amount of sun cream purchased. But they're not causing each other. They are both caused by the weather change. Or maybe we find a new type of frozen zero-calorie yogurt health drink is launched on the marketplace, and the sales start to go up. And as the sales start to go up, the number of retailers selling it goes up. And as the number of retailers selling it goes up, it in turn drives up physical availability and mental availability for the product. So the sales go up. That's a feedback loop. Once it's started, it's not strictly true to say sales are increasing retail outlets or retail outlets are increasing sales. They're both feedback increasing each other. But if X is correlated with Y in our data, we should investigate Y. We get too much data these days. It's really difficult to find the patterns. So we're looking for some clues. And if we see some strong correlations, we should go there and investigate. Is X causing Y or Y causing X, or are they both being caused by something else? Or is there a feedback loop, or is it just chance? And here's a great example of how important that can be. Back in 1950, UK researchers Richard Dahl, Austin Bradford Hill conducted research for the Medical Research Council, and they discovered a correlation between the amount of tobacco smoked and lung cancer. At the time, they were actually searching for a link between new types of tarmac and lung cancer, because lung cancer had been increasing, and they were trying to identify what it might be, what was causing this increase in lung cancer. And there had been large amounts of the country, tarmac and new types of tarmac were being used. But when they started looking at all the correlations, the one that stood out was the link between tobacco smoke and lung cancer. And this was quite a surprise. Tobacco had previously sometimes been thought to be healthy. They published their findings in 1950 in the British Medical Journal. 1954, there was a bigger study commissioned, the British Doctors Study, and that confirmed the correlation. And that was the first time the government, the UK government, issued advice that smoking and cancer were related. Now, in this case, they didn't know that did smoking cause cancer, did cancer cause smoking, or did something else cause people to smoke and have cancer. That final one is a possibility. It's very unlikely when we look at the data that being likely to get cancer makes you more likely to smoke. So that one could be disregarded, but the possibility that there were other factors driving both was something that had to be looked into. And it wasn't until proof had been found from science that showed the causative mechanism that everything was tied together. But luckily, many, many initiatives were taken on the basis of the correlation, which will have saved hundreds of millions of lives. So, correlation does not imply causality, but I've highlighted it in red and put it in big bold font. When you see a correlation, investigate the why. And a lot of times you'll find it's what we call a spurious correlation, a correlation that doesn't really exist. It's just luck or chance. And there's a whole website devoted to these, spuriouscorrelations.com. And here's a lovely example. The number of people who drowned by falling into a swimming pool correlates really highly with the number of films Nicolas Cage has appeared in. Now, clearly, that is a spurious correlation. This one is more interesting. This was actually appeared as a spoof in a medical journal and was then picked up by some newspapers as being real news. And what we have along the bottom scale is how much chocolate is consumed. I think the year was 2012, in kilograms per year per head of population. And so you can see that Germany and Switzerland are consuming more kilograms of chocolate per year than anybody else. China is consuming less. And on the vertical scale, we have the number of Nobel Prizes won per 10 million of population. Obviously, big countries win more Nobel Prizes than small countries, so we need to do something to put it on an even scale. And we see that the R is really impressively high. It's 0.79, which would be an R squared of 63%. Have a look at the page graphically, and it looks like something really serious is going on. But it's not that chocolate consumption is causing Nobel Prizes, even though there is scientific evidence to show that if you eat chocolate and then do an IQ test, you will score marginally higher in the short term than a control cell that has not eaten the chocolate. Now, what is going on here is that they are both driven by some other factors. The longer a country has had a developed economy and an industrial revolution, the longer it's had universities, the higher its score on Nobel Prizes. And just to confirm that point about that chocolate is not the driver, as I said, the chocolate consumption here is 2012. Some of those Nobel Prizes were won in 1930 and 1940. There is no way that consuming chocolate in 2012 makes you more likely to win a Nobel Prize in 2030. So we can see that it's not a simple X causes Y relationship. So that's the causes of correlation. So let's get to the real essence of today's presentation, using it to find stories with correlation. And as I said, because we now have so much data, we need to use tools that are going to show us where the interesting things in the data are. So we're going to use means, we're going to use standard deviations, and we're going to use counts to give us some data. But actually with a large data set, that gives us too much data. So we want to use some techniques that are going to allow interesting things to bubble to the top and give us some patterns. So what we're trying to do, and things like correlation, will help us map the data. They will show us which bits are similar. They will give us some standout peaks. They will tell us over here is water, over here is something quite interesting. Please have a look at it to see whether that is where the treasure will be buried. So here's an example piece of data. I've heavenly disguised the real nature of this data, but we've got NPS on a 1 to 10 scale in the first column of data, and then we have some satisfaction ratings, a 1 to 7 satisfaction scale with how good was the bed, how good was the restaurant, how good was the price. And there's a lot of data there, and we could do crosstabs and breaks, but we do a lot of things trying to find out what was going on. So one of the things we can do is we can say, well, what is the correlation between the Net Promoter Score, the NPS score, and all the other features? And we see immediately that the bed comes out really highly at 0.8, and at the bottom of the scale, there's the minibar coming out as a 0.2 correlation and some numbers in between. Well, if you've seen any of my other videos around finding the message in the data, the story in the data, you'll know that I'm a big fan of sorting the data in order to be able to see those patterns. So we'll do that, and what we can see now is that bed is by far the strongest, then location, restaurant, then there's a jump down and we have a bit of a pair of the check-in process and the checkout process, price, bathroom, internet, TV, minibar. So we've got a bit of a system to that. But actually, it's very hard with our brain and our eye to understand what does bed 8, 0.8, mean compared with location 0.62, mean compared with the internet at 0.27, because these numbers are not linear numbers. They are not something that intuitively makes sense. So what we do is we square them. So now they are the ratios of the shared variance over the total variance. So in the case of the bed, 64% of the variance that is shared between NPS and the bed is also the total variance. So it's a large amount of that variance. If we look down, we've got a nice round number with bathroom. Bathroom is 10%. So we can say that price is 1.5 times as associated with it with NPS as the bathroom is. We can say that the restaurant at 34% compared with 10% is 3.4% times as associated. We can say that the bedroom is 6.4% times as associated. So now we have a sort of importance measure. We don't know whether NPS is driving the score or the score is driving NPS or some combination, but we now have a whole set of associations which we can use. And we will often take the jump and say, well, let's treat that R squared value as a measure of derived importance. And we've got the actual satisfaction scores with all of those things for this hotel as well, and we can plot them on a quadrant. And in the top right section, we can see things that are highly important and where there is a high satisfaction. So bed, location, check-in and check-out are all things that this hotel is getting right. Top left quadrant are things that are important, but the hotel is not getting them right. There's low satisfaction, and the restaurant would be a case of something which is not delivering against an important attribute. On the bottom left, we have two things where there's low satisfaction but low importance: minibar and price. Why might price be important, not so important? Well, we're interviewing employees perhaps who are visiting at the hotel. They might think the price is a rotten price, but actually it's having no impact on their appreciation of the hotel because it's not coming out of their pocket. And in the bottom right, we have things that the hotel is getting right, but which are of low importance to the customer: the bathroom, internet, and TV. So we start to be able to tell a bit of a story, and we would then dive into the data to see whether or not that picture was true. Because when we're story finding, first of all, we get some indication from the correlation and then things like this quadrant map, but then you need to verify it, read some of the open ends, have a look at some of the other patterns in the data to make sure that is the correct interpretation. If we go back to these R squared values and we sum them up, we see they come to 214%. So they can't be simple importance measures. What's going on there? Why is there this increase? Why is it more than 100%? And the reason for that is that some of these attributes, or all of these attributes, are correlated with each other. They are measuring the same thing. So the importance gets counted more than once. We call this multicollinearity. And multicollinearity, when it's really bad, is a nuisance because it messes up our numbers. It messes up our regression equations. It messes up our segmentation and cluster analysis. So we're always keeping our eyes open for whether we have multicollinearity. And if we do have it, is it bad enough to mess up the numbers? So it's a great idea to have a look at the correlation matrix. Here are all of the attributes correlated with all of the attributes, and I've put a bit of color coding in. So if we start on the far right-hand side, we have the minibar. And the minibar, the satisfaction with the minibar is hardly correlated with anything else. It's quite an independent feature. If we go along to, let's say, the TV column in the middle, again, it's correlated a bit with price and the internet and the minibar, but not a lot. Now let's go to that bed column, and what we're seeing there is bed is correlated with almost everything. Now, with experience, that starts to suggest to us that the bed actually isn't a rating of the bed, it's a rating with how good was the hotel experience. People are not using perhaps the specificity about the bed, because why should the bed be so correlated with the restaurant and the check-in and the check-out and the location and the bathroom? So there could be a bit of a halo effect going on with how the bed is being interpreted. So we might want to be careful in how we use that. That statement we might have had earlier, that the most important thing is the bed, might want to be tempered a little bit if in fact the bed is a shorthand statement for, yeah, the bed, the bedroom, the sleeping, the experience was all fine. And if we look across to about the middle of the table, you get the check-in column, and you'll see there we've got a couple of 0.71s. So the check-in and the check-out are highly correlated with each other, about 50% in common. But also that means about 50% not in common. So there are some things which are distinctive about the two processes, and we might find there's scope to improve one or the other. So that is how we might use correlation. We use it to assess some links. We use it to show us some patterns. We use it to show the interactions between variables. And then we dive into the story. But of course, there are deeper techniques. And I was at a presentation the other day when Jeffrey Henning of the University of Georgia's MRII course was talking about correlation and some other techniques, and used it as the description, it's a gateway drug to advanced analytics. I think that's a great way of looking at it. Once you start using correlation to understand some of those slightly hidden patterns, you're beginning to take a path that's going to lead you to use more and more techniques when they're necessary to find the hidden patterns. So we can run factor analysis on that data, the same data, and it would suggest there are 4 factors. There is the check-in, TV, check-out, bed factor, and that's the biggest one. It accounts for, if you look at the bottom, 29% of all the information in that data set is accounted for by that first factor. We can then have a second factor, the bathroom and the minibar, a couple of things in the room. That accounts for some more of the variation. We go to factor 3, price, restaurant, and location, and the internet remains as a quite independent feature, adding 11%. And these 4 factors between them would explain 75% of that information, the data, which is why we had that multicollinearity. It's why it came to 214% when we added all of the R-squared values. There's a blog and a webinar on factor analysis. If you want to learn more about factor analysis, then visit the NewMR webinar and you will be able to find out about that too. Drivers of choice, importance, etc. So I showed a method of using correlation to do drivers of choice. Now, most marketing scientists would prefer not to. It's very easy to do it. It is very stable. When you do it on this year and then you do it next year on similar data and the following year on similar data, you get very similar results. But it's not rigorous, which is why Jeffrey Henning described it as a gateway drug for advanced analytics. Because you can use regression, you can use things called Shapley values, latent class, conjoint analysis, path analysis. And if you want to read more about those, then I would advise you to have a look at Chuck Chakrapani's book or the University of Georgia's course on advanced analytics. Now I've mentioned regression, it's probably worth talking about what the difference is, because sometimes people are a little bit confused about the difference between correlation and regression. So this is a regression equation, and what this shows us is that we can predict the value of y from the value of x. If we multiply the x value by 2 and we add 1, then we get the y value. So let's go to the x value of 2 on the bottom. We multiply that by 2. That will give us 4. We add 1, we get 5. And if we read up on the blue line, we can see that, yes, x equals 2 gives us y equals 5. Similarly, if we say, well, let's put x as 7. 2 times 7 is 14, plus 1 is 15. If we go to 7 on the x-axis, we read up, then we see that comes to 15 on the y-axis. So that is the regression equation at work. Now this data is interesting because it has the same regression equation, 2x plus 1. But now the blue dots don't sit on the line, and you can see the r-squared has gone from 1, which is when the dots were exactly on the line, to now 0.67. There's 67% of the information is in common, 33% is not. And if you have a look now on this right-hand chart and read across to 7, we know that it should give us 15 on the y-axis, but actually it gives us about 10, because that's the wobble, the lack of good fit. So this is another use of correlation. We use this as an R-squared, and it tells us how good the model is at matching the data we have. It doesn't tell us how good the model is in terms of predicting the real world, but it does tell us how good is this model for predicting the data we've observed. And on this case, you might think visually that was pretty poor. It was for the value of X of 7, it predicted a 10 instead of a 15, but actually that's a 67% goodness of fit, and you will quite often have to live with worse than that when you're working with real data. So, to summarize, what are the uses of correlation? We use it to show patterns in the data, association between items and associations between attributes. We use it as a measure of importance, attributes that correlate with an outcome, for example, satisfaction or purchase or churn or probability of renewal. Any of these things might be more important than attributes that do not correlate. We can use it to suggest areas of investigation. The link between smoking and lung cancer started as correlation. Now, obviously, we're unlikely to cure world poverty in the area of market research, but it will give us some indications of things that are worth discovering, looking at, and seeing if there is a causal link. And in the form of R-squared, we use it to assess the quality of models, usually in terms of consistency rather than validity. And we'll perhaps have another webinar on the difference between validity, reliability, consistency, and so on. So thank you very much for your time. My name's Ray Poynter, and you can connect with me on Twitter and LinkedIn via these links.